downtown Montreal, where masks are a must, but where we are continuously bathed in the iridescent glow of 5 gigahertz microwave radiation, supporting a robust and bounteous symmetric 300 megabits per second upload-download data stream as strong as the St. Lawrence. Welcome to this, the 38th annual Anna I. McPherson Public Lecture in Physics. Before I pass to the department chair to say a few words about the history of this lecture series, I will quickly explain the plan. First, everyone in the Zoom session should take note that your image and/or voice may be recorded and broadcast live via YouTube. If you prefer not to be recorded or live streamed, please log out of the Zoom session and join us via YouTube. This evening, we will have a 45-minute talk, followed by 30 minutes of questions. We will be taking questions both from within the Zoom session and from the YouTube chat. To ask a question from within the Zoom session, please use the raise hand feature of Zoom. That will put your name at the top of the participants list. I will then call on you to unmute yourself, turn on your video, and ask your question. When you are done with the question, please lower your hand to bring others to the top. During the talk, participants in the Zoom session will remain muted and will not be allowed to unmute. At the end of the talk, you'll be freely available to unmute, but please do not do so unless you are called upon. To ask a question in YouTube, please enter it into the chat. The questions will be relayed to me by my associate following the talk. It is very likely that we will not be able to field all questions this evening due to the time constraints. If your question does not make it in, please feel free to join us again tomorrow afternoon at 3:30 p.m. for the scientific lecture. With that, I will now pass to Professor Sangyong Jeon, the chair of the Department of Physics, to say a few words about Anna McPherson and the history of the McPherson lectures. Professor Jeon.
Thank you, Bill. Okay, welcome to the 2020 edition of Anna McPherson lecture in the Department of Physics at McGill. I'm Sangyong Jeon. I'm the chair of the department. I'm very happy to see you all here even in these difficult times. Anna Isabel McPherson had a long association with McGill that extended over a period of 60 years. She obtained her bachelor's degree with first-class honors in mathematics and physics from McGill in 1921, winning the Ann Morrison Gold Medal. That medal is still one of the most prestigious awards for undergraduate students in McGill today, even today. She then went on to obtain a master's degree from McGill under the supervision of Arthur Eves, who was a colleague of Ernest Rutherford. After that, she taught mathematics for a time in a local high school, then went to the University of Chicago to receive her PhD in 1933 under the supervision of A.J. Dempster. In 1940, she joined McGill as a demonstrator and was subsequently appointed as an instructor in the wartime program on the training of radio mechanics. This was followed by an appointment as a sessional lecturer in 1943, then as a full-time lecturer also in 1943, and then assistant professor in 1947 and associate professor in 1954. After retirement in 1970, the university invited her to become an honorary visiting professor, a post that she held until her death in 1979. During a long career at McGill, she taught and helped a very large number of students. She had a reputation as an excellent teacher. Optics was her specialty, and her advanced light laboratory represented one of the finest opportunities for training in classical optics available anywhere at the time. In all areas of classical physics, her background and her ability to teach made an important impact on McGill's undergraduate physics program in the years following the Second World War. Her contribution to McGill was not only in teaching, research, and counseling. Upon her death in November 1979, she gave a large sum of money to the university to be used for medical research and for the Department of Physics. The department uses the revenue from this money to support research and also establish the Anna I. McPherson Lecture in Physics in her honor. The mandate of these lectures is to bring distinguished physicists to the department for a few days to give lectures as well as to meet with staff and with students. In establishing this lectureship and by naming the small astronomical observatory of the Department of Physics in her memory, the members of the Department of Physics seek to acknowledge her outstanding generosity and her many valued academic contributions. Her legacy lives on in the many students she educated and the inspiration it has provided for many generations of young physicists. Now I'm delighted to introduce you to Professor Jack Childress Sankey, in parentheses, who will introduce the 2020 Anna McPherson lecture. Thank you. To you, Jack.
Okay, thank you very much, Sangyong. So it's an especially wonderful pleasure to introduce Professor Nergis Mavalvala as our 2020 McPherson lecturer. I first became aware of Nergis when I was a totally green optomechanics postdoc in 2008, went to a conference and one of her students, Thomas Corbett, stood up and gave an invited talk about laser cooling of massive objects and how they created a column of light that was stiffer than a piece of diamond. So my brain was full of fireworks at that point, and I approached him and started asking a series of truly stupid questions. Can you do this? What about this? All of which received generous, thoughtful answers. And now, with the caveats that it's been about 12 years since the encounter, and that I've certainly suffered modest brain damage from toddler-induced sleep deprivation, this memory currently includes Nergis standing by with a huge smile, occasionally interjecting a fun thought or new consideration to the conversation. This interaction certainly occurred on subsequent iterations of the conference. So in later years, I often noticed at these conferences exactly one baseball cap in the audience, and the owner of said cap or her students would consistently present something that blew my mind. I was lucky enough to chat with Nergis herself on many occasions over the years. I continued my practice of asking truly stupid questions, and she consistently supplied enthusiastic and thoughtful responses, just like the students that she'd trained. Fast forward to about 2016, well, to exactly 2016, LIGO announces their first ever measurement of a gravitational wave, the first signal from space that is not electromagnetic, a discovery that is, I would say, of century scale importance for sure, and possibly the most important result that I may ever see in my lifetime. The McGill physics department stuffed itself into a small room in the McGill Space Institute. There were Snickers, and we watched the data and its implications unfold with dropped jaws. Like, I literally found myself shutting my own mouth. So as a proud, mindless consumer born in the United States, I then promptly bought Kip Thorne's book and started really learning about how hard this team had been pounding away on this seemingly impossible problem, literally squeezing every last bit of sensitivity from their kilometer scale interferometer, and the role that Professor Mavalvala played. I later asked Nergis how she found the courage to pursue something for 2 decades that may very well simply have produced absolutely nothing. And her answer, in more elegant words than I'm going to use right now, was that it took no courage at all, because the team just loves building precision measurements and playing with the toys. I'll note that the impact of LIGO's work extends far beyond the field, and you'll find their technology and technology based on their technology in a lot of places. Anyway, all this to say that Nergis has been a hero of mine since 2008. The results from her group have appeared near the top of every talk I've given in the field. And as it turns out, I'm not alone. So a bit of background. Since coming to the United States, Nergis went to Wellesley College, and already somehow she managed to publish in an APS journal at a time when this was very uncommon. She got her bachelor in 1990. She joined Rainier Weiss's group at MIT, helping lay the foundational work for LIGO. In 1997, she got her PhD, went to Caltech for a postdoc looking at cosmic microwave background. And then in 2002, the MIT physics department, clearly missing her, stole her back, and they won. She's now the Curtis and Kathleen Marble Professor of Astrophysics and the Dean of Science at MIT. She's got a long list of awards. Notably, she's a MacArthur Fellow, a Sloan Fellow, an APS Fellow, an OSA Fellow. And in 2014, she was the LGBTQ Scientist of the Year. And in 2017, she was elected to the National Academy of Sciences. So this list goes on, and I was interested to find that even the Pakistani government, including the Prime Minister, singled her out on a few occasions as a scientific hero. So Professor Mavalvala is giving the McPherson lectures because of her numerous awesome contributions to the gravitational wave astronomy, quantum limited measurement, and the optical control of the motion of solid objects. Her team's most recent breakthroughs I'd like to highlight are particularly impressive. They've created a tabletop room temperature microphone that is sensitive enough to hear the quantum hiss of photons bouncing off of its surface. A year after this or so, they used this response to create so-called squeezed light that can push interferometer sensitivities below a thing called the standard quantum limit. I'm kind of advertising. I hope some of you can make it to tomorrow's scientific lecture. This is truly amazing work. Okay, so after I apologize to Nergis for making her uncomfortable, I'm sorry. Please join me in welcoming Professor Mavalvala to the stage. Come on, people. Right. The global pandemic. Well, I will take the attendance number as a proxy for the number of decibels we would be experiencing in the lecture hall at this moment. So without further ado, Nergis, you can take the floor.
Well, thank you very, very much, Jack. And thank you also, Sangyong and Bill, for the invitation to give the Anna McPherson lecture. I did not know Anna McPherson's story. It makes me all the more proud to be giving a lecture that's named for her. I also wanted to say I have never found Jack's question stupid. In fact, I find no questions stupid. So please ask me questions at the end of the talk. I do find some ideas stupid, and hydroxychloroquine might be one. Injecting yourself with bleach might be another. But that's not what we're here for today. Let me tell you about something much, much more positive than those difficult ideas that are coming out of the southern border to Canada. It's about gravitational waves, and really, this is a story of a discovery. And this is a story that's not about a single discovery, as I hope I will convince you, but about a series of discoveries that have opened up a completely new way for us to look at the universe, and that is gravitational waves. Now, before I go any further in my talk, I do want to acknowledge that much of the data I'll show you, the instruments I'm going to describe, the people who I'll weave into my story, this is all part of a large group of scientists, the LIGO and Virgo collaborations. Over 1,000 scientists have participated in this work. So when we talk about opening a new window into the universe, we must first consider what was the old window into the universe. And it turns out the old window into the universe was cosmic light. Much of what we know about our universe to this date has come because light from the distant stars and galaxies, and even out to the edge of the observable universe in the form of cosmic microwaves, has informed us about what goes on in the universe. And one very beautiful depiction of this is this object. And this is a supernova remnant, Cassiopeia A. What this object is this is a picture that's taken with light in multiple colors. If you look at the reddish colors, that's infrared light. The greens and yellows are visible light. And then the purples and blues towards the very edge of the picture are actually X-ray light, so the most energetic form of light. And one of the things that's very beautiful about this picture is that when you look at an object in this multicolor way, you learn a great deal about it. So what was this object? This object was once upon a time a star, not very different from our own sun. And as this star ran out of the nuclear fuel that stars burn to keep them buoyant against their own gravity. So typically a star is a nice big orb because as it burns nuclear fuel, the light flows outwards and the radiation pressure from that light is acting against the gravity that's trying to pull the star's material in. When the nuclear light source burns out, the star has fused up to heavier elements that don't burn anymore. The star collapses, and in that process, there's an explosion and sheds some of its material outwards, and that's what all these colored gases and dust and material are. Now, if you look very, very carefully at the very center of the object right here of the picture, you'll see a little blue object. And this blue object is only visible in the form of X-rays. And it is a neutron star. It is the newly born object that was born out of the implosion of this parent star. Now, if the parent star is about twice the mass of our sun or less, it will form typically a neutron star. If it's a fair bit heavier, if it's a few times the mass of our sun, as it implodes, it continues to collapse and it becomes a black hole. So lesson number one, neutron stars and black holes are cousins of each other. And they're in this particular class of black holes are formed by the collapse of stars like our own sun, a few times heavier typically. So that's one of the ways in which we have known about our universe. Now, if this object hadn't been a neutron star, but in fact was a black hole, if it had collapsed all the way down to a black hole, how might we observe it? Well, in some cases, we can observe black holes because of the gas and dust around them that's glowing as they're sucking it in. But in most cases, black holes are black. They are objects that have so much gravity that even light can't escape. And therefore, if we wanted to observe some of these most mysterious objects in the universe, we need some other messenger. Light doesn't do it for us. And there comes our new messenger, and that is gravity's messenger. So to understand gravity's messenger, we need to understand gravity. So let's take a look where many of us have been introduced to gravity, not just because we can jump and are pulled immediately back down to the earth, but also more formally in the form of Newton's universal law of gravitation. And Newton in the 17th century gave us this beautiful quantitative description of gravity that says, well, if you have two massive objects and you place them a distance r away from each other, then they experience a mutual force that's proportional to each of their masses and inversely proportional to the square of their distance. Now, Newton himself worried about a phenomenon called action at a distance. Newton, and even before him, Aristotle, worried, how does this object one know about object two? How do they influence each other? What mediates that interaction? And that question did not get solved until our next hero of gravity in the early 20th century, and that was Einstein. And Einstein told us to stop thinking about gravity as a force, but instead to think about gravity as geometry. Gravity is the actual curvature or warpage of space-time itself. Now, like Newton, Einstein also wrote a formula, but his formula, it turns out, was one of the most beastly formulas ever written. It has been very difficult to solve, and throughout my talk, you will see this as a recurring theme, that beautiful as Einstein's formulation was, it's also been very difficult to get exact solutions to this more exact way of thinking about gravity. So Einstein's picture was, when you have space-time, empty space-time doesn't just sit around doing nothing. Empty space-time, when you put a massive object in empty space-time, it will curve that space-time. And in fact, if you take that massive object and you actually oscillate it or accelerate it, it will emanate ripples on the space-time itself in the form of waves that would look like this. You can think of this very much like you might think about dropping a rock on the surface of a pond and ripples spread out from where you drop the rock. Space-time does that as well when you put massive objects there, in particular massive objects like neutron stars and black holes that have enough gravity to actually warp the space-time sufficiently and make these waves as they orbit each other. So Einstein himself, even though he proposed this and he wrote this very exact theory that we're still not finding much fault with as we do more and more precise measurements, he himself was quite ambivalent about it. He formulated this mathematical framework of those beastly set of equations I told you about between 1915 and 1918 in his general theory of relativity. In 1918, Schwarzschild proposed these stars that could have so much mass in a small volume that even light couldn't escape their gravity. In Einstein didn't like these dark stars at all. They were called dark stars at the time. So that was known already by 1918 that these could exist, but Einstein didn't think nature would do such a thing. Einstein also wasn't so sure about these gravitational waves. Even though they popped out of his equations, he really struggled with whether they are a mathematical artifact or could nature really do such a thing. And in fact, in 1936, he wrote a paper retracting their very existence, that gravitational waves couldn't exist. And then in the same year, through discussions with other scientists, he retracted the retraction. And you could see this was not a settled subject at all until about 1957, when through the work of several others, people began to understand that the mathematics was right and this should actually happen in nature. But now I'm going to make a very important statement, which is that experiment and observation in the end always have the final say. No matter how beautiful the theory and the mathematics, we have to check, does nature really do this? And those observations came in 1934. Body and Zwicky actually theorized that the neutron stars could exist. These are stars that are made up of neutrons. In 1967, people proposed, Piccini and Gould proposed that these neutron stars could spin rapidly about their axes. And because of the fact that they were made of neutrons and they spun very rapidly, they would have extremely strong magnetic fields. And therefore, the light that was emitted by them would be beamed like the light of a light pulse from a lighthouse. In the very same year, in 1967, the first pulsars, these rapidly rotating neutron stars, were observed by Bell and Hewish. And then in 1969, this man, pictured here, Joe Weber, announced the first detection of gravitational waves using a device that was a big chunk of metal that was instrumented with very precise sensors to measure when the metal rings. So the whole idea was that a gravitational wave would come through and it would set the metal ringing just the same way as you might ping a wine glass and it rings. And the instrumentation around it was to hear that ringing. That turned out to not be a verifiable claim, but Weber's announcement set the world on fire in terms of being able to think about looking for gravitational waves. Eventually, in 1971, the first black holes were discovered. And then in 1974, a system was discovered with two neutron stars, where one of the neutron stars was a pulsar. So it was this lighthouse. And as these two neutron stars orbited each other, you could count the light pulses coming from the pulsar and time them. Now, when our own Earth goes around the sun, we just close on our orbit year after year, the same orbit. Not so for these highly gravitational systems like a binary neutron star. There, because this system is radiating gravitational waves, those waves carry away energy, and that energy comes from the orbit. So these stars are getting closer and closer to each other and spinning around, orbiting each other faster and faster, and eventually they collide. When Hulse and Taylor discovered this system, they were able to then show that these two stars, these two neutron stars, were getting closer to each other. They made this measurement. You can see this graph shows measurements from 1974 to 2005. And the vertical axis is simply, you can think of it as the size of the orbit of the stars. And what you see is that their data are the dots. And the solid line is the exact prediction from Einstein's general relativity for how this system should behave if it's radiating away gravitational waves. And this is widely seen as sort of settling the debate about whether gravitational waves exist and could be radiated. And in fact, in 1993, Hulse and Taylor won the Nobel Prize for this discovery. But I do want to take a step back and give a shout out to Einstein again. I mean, his ambivalence was justified. The first observational evidence for neutron stars and black holes didn't come in his lifetime. He died in 1955, and these objects came around in 1967 to 1971. But the most remarkable thing when I think about this history is that even so, his theory of general relativity made very firm predictions about gravity and space-time and black holes. So now we fast forward to 2005 and beyond, and finally people have made sufficient progress with supercomputers that they can start to solve some simple cases of two black holes orbiting each other using Einstein's equations. And so these are supercomputer simulations that show two black holes, and you can see when they're far apart from each other, they're just orbiting each other, and you can see the funnels of space-time distortion under each black hole. But because these black holes are radiating gravitational waves, they're going to lose energy. Their orbits are going to get closer to each other. They're going to orbit faster and faster, and eventually they will collide. And you can see that depicted in this two-dimensional cut. So the space-time is shown in two dimensions, the warpage of space-time. The space is shown in two dimensions, and the colors show time. So you can see as they get closer and closer to each other, these two funnels of the black hole space-times are starting to sort of merge with each other. And at the moment that the two black holes touch, you see the spectacular warpage of space-time. On the bottom is shown the signal accumulating. And then eventually these two black holes merge into a single black hole, and they wobble slightly, and then they become quiescent, and in most cases sort of never to be seen or heard from again. And the gravitational waves, they propagate out into the universe. And you can see from the listing here that this was the outcome of really decades of work by computational physicists and mathematicians in solving Einstein's equations to start to be able to do these kinds of simulations. And the big breakthroughs came in 2005 and later. But it wasn't always so. Now we step back to say the late 1960s, and at that time, this man, Kip Thorne, who's a professor at Caltech, was thinking about what would a gravitational wave look like from these newly discovered neutron star pairs. And he was among the first to put a scale on it. He said, well, if you take these neutron stars, they're typically about the mass of our sun, and you put them in orbit around each other, and you put them in a galaxy not too far from our own, then the strength of the gravitational wave signal, which is called a strain, would be about 10 to the minus 21. And he even showed that they would have this particular shape, which is called a chirp. It's basically a sinusoidal signal that's growing in amplitude and in frequency. It's getting faster and bigger as time passes. At the same time, also in the late 1960s and early 1970s, people were thinking about how one might detect gravitational waves. Remember 1969, Weber's claims had just come out. So to understand how we detect gravitational waves, we should think a little bit about what do they do here on the Earth, not at the black holes that are colliding, but here on the Earth. And here on the Earth, what they do is they're ripples of space-time. They like the rock that was dropped at the center of the pond, and then the ripple travels outward. These ripples of space-time, they travel at the speed of light. That's a prediction of Einstein's. And most importantly, they stretch and compress the space-time itself. And what that means is that as they propagate through space, they're constantly pulling space apart and pushing it back together again, perpendicular to their direction of motion. What they do is that they change the distances between massive objects. And if you have a distance between a massive object that's distance L, then the amount by which that distance will change is proportional to the amplitude of the wave h and to the distance L itself. So we could put a scale on this by using me, for example, as a gravitational wave, or any human. A human typically has a length of about a meter. Kip Thorne had already predicted for us that the amplitude of the wave would be apart in 10 to the 21. And that quickly tells you that a human scale object would change its height, like me, a meter scale object would change its height by 10 to the minus 21 meters. That's the scale on which we, the weakness of this effect, which is that it's a very, very small effect. 10 to the minus 21 meters, just to put it in perspective, is a million times smaller than a proton. So it's a very, very small change in distance for even over the length of a human scale object. But in the late 1960s and early 1970s, this man, Ray Weiss, understood that there was a device that would be capable of measuring very, very small changes in distance. And that device is shown here on the right. It's an interferometer. And what it is you start off with a laser at the left side, and this laser splits its light into two halves on a beam splitter. And each half of the light travels a certain distance, hits a mirror, reflects from that mirror, and comes back to the beam splitter. And then by whether the light from the two arms interferes constructively or destructively, whether the waves of light add up with each other or cancel each other, you can get lots of light at the output or no light at the output, and everything in between. This device is called an interferometer, and Ray Weiss understood that you could use an interferometer perhaps to achieve sufficient precision to measure this very weak effect from the gravitational waves. The greatest contribution here was not just to recognize that the interferometer was a good device, but Ray Weiss also understood that to make this measurement possible, you had to make the interferometer long. And so we already know that the change in length I told you was proportional to the amplitude of the wave h sub GW times the length of whatever space-time distance you're covering. So he said, don't make this interferometer a meter long as would fit in your lab, make it kilometers long. So he proposed a 4,000 meter or 4 kilometer long detector. And then you would have to make a measurement and a change in distance between the mirrors of the interferometer of 10 to the minus 18 meters. And that's only 1,000 times smaller than a proton. And in 1972, Ray Weiss said, yeah, we can do that. And he laid out a roadmap for how to do that. And since then, this has been the endeavor of the field to be able to build interferometers that were precise enough, had sufficient precision to make the measurement. We fast forward again to the 1990s. So that was Weiss's work was in 1970s. In the 1990s, LIGO was funded by the National Science Foundation. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. And you can see on the top right is the cartoon of the interferometer that I showed you, the animation. And then these two photographs are the 4 kilometer long aerial views of the 4 kilometer long L-shaped detectors of LIGO, one in Washington State and one in Louisiana. Now, to make LIGO work, you really need to do two things. You need to do very many more, but two things conceptually. And if you can get those two things right, you'll make a measurement of a gravitational wave. So the first thing is you have to take the mirrors of LIGO. See, the mirrors that reflect the light are also the same objects that are going to be moving apart and together because of the passing of the gravitational wave. Now, the gravitational wave is going to move those mirrors over those 4 kilometers by 10 to the minus 18 meters. That's the number we just calculated. If you just take a mirror and let it just sit in a decent laboratory environment, the mirror will move by about a micron or 10 to the minus 6 meters. So that's your first factor of 1 trillion. You actually have to shield or isolate the mirrors of the interferometer by a factor of 1 trillion. And in the case of LIGO, that's done in two ways. The one is that these mirrors are mounted on a vibration isolation platform. And that kind of works very much like you might think about a noise cancellation headsets, like almost like the ones that I'm wearing, where you measure the motion outside of this platform, and then you actually push on the platform to cancel that motion. So you add the same motion that you measure back to the platform, but with a minus sign. So you cancel out the motion, and that gets you part of the way. It gets you to about 10 to the minus 13 meters. And then you take the mirrors of LIGO, which are these 40 kilogram, 35 centimeter diameter objects, and you hang them from a cascade of pendulums. And it turns out that pendulums are very good filters for vibrations or noise at the top of the pendulum where you have the string. That noise doesn't transmit down to the plumb bob if you design it with care. And that gets you down to the 10 to the minus 18 meters. So now you have a mirror that's really still enough that you can measure its motion due to the gravitational wave and not due to earthly effects. And now you have this other challenge, which is how do you measure such a small motion? And to do that, that's the L in LIGO, that's the laser light. The wavelength of the laser is the tick marks on our ruler. You can think of it that way. So the laser that we use is near infrared, so 1 micron, so 10 to the minus 6 meters. And we have the challenge of measuring at the level of 10 to the motion at the level of 10 to the minus 18 meters. So that's your second factor of a trillion. You're trying to make a measurement that's 1 trillion times more precise than the spacing of the tick marks of your ruler. And the way that we get around that in LIGO is that we use lots and lots of light, lots of photon, high power, so that you can average over the fluctuations in your tick marks. And so in LIGO, we use a very powerful laser, and eventually, by the time everything is running, we should have almost a megawatt of laser light in the interferometer, and that lets you make the measurement precisely enough. All of this has been funded by the NSF, and the person who was really credited with building the LIGO observatories was this man, Barry Barish. Okay. The LIGO is not the only game in town. There's a global network of detectors. So the 2 LIGO detectors are in the United States. I already showed those. There's a 3-kilometer-long detector called Virgo in Italy, and there is a 3-kilometer-long detector in Japan called Kagra. That the Virgo and Kagra are both operational at different levels of sensitivity. Virgo has partnered over the years with LIGO and is competitive in sensitivity. Kagra is still coming up, and then a proposed detector in India as well. Now, fast forward from the building of LIGO, which was in the 1990s, to September 14, 2015, when the first binary black hole collision was detected by LIGO. And this is now a very iconic signal. The picture here is 2 black holes. They orbit each other, they collide. The gravitational waves that were radiated pass across a large distance in the universe. And miraculously, they find their way to our part of the universe. And indeed, they actually come through the Earth. And you can see the wave arrives first in Louisiana, and about 7 milliseconds later, it passes through the Washington detectors of LIGO. Now, of course, the Earth didn't wobble quite that much. This is a highly exaggerated effect, but that was the trajectory of the wave. And here is the signals that were detected by LIGO. And I want to say just a few things about that. So if you look at the vertical axis, you see strain or amplitude of the gravitational wave signal in units of 10 to the minus 21. And if you look at the part where the amplitude was the largest, that corresponds to a strain of 10 to the minus 21. And that's an enormous check mark for Kip Thorne. He told us this in the late 1960s, that when you look for neutron stars and black holes in a galaxy not too far from our own, that's the size of signal you should expect. If you ask how much did the mirrors of LIGO move when this black hole signal was detected, they moved by a few times 10 to the minus 18 meters, and that's an enormous check mark for Ray Weiss, who also told us as early as 1972 how to build interferometers that would have that kind of sensitivity to displacement. Now, what can we learn from this signal? Well, in a very cartoonish way, you can see this as a model of the very same signal. And by looking at how the frequency changes as the signal evolves, we can actually infer the mass of the black holes in some convoluted way. This is a simplified picture. Once you know the mass, by looking at the amplitude, you can tell how far this black hole pair was from us, the observers. And then finally, by looking at this last phase of the signal where the single black hole forms, it wobbles a little and then kind of rings down and becomes quiescent, from that process, you can tell what the mass and spin of this newly formed final black hole was. And from that, we could tell the story of these 2 black holes. And what we could say was that once upon a time, 1.3 billion light years ago, there existed two black holes. And exactly as Einstein's general relativity instructed them to, they orbited each other. And as they lost orbital energy to gravitational waves, they eventually collided with each other and formed a single quiescent black hole. And in that process, and through that signal that we saw, what we could tell about that black hole was that the masses of the two black holes that started off was about 30 times the mass of our sun. At the time that they collided with each other, these 30 solar mass black holes were traveling at half the speed of light. And you really have to sort of sit down and think about that. Objects that are 30 times the mass of our sun traveling at nearly at the speed of light. This is nature at its most spectacular and violent. The system was 1.3 billion light years away. And remarkably, the newly formed black hole was 3 solar masses lighter than the two parents. And 3 times the mass of our sun was radiated away in gravitational waves in this collision of the two black holes. And what we learned, of course, is also that the two initial black holes did not live happily ever after. In fact, they're very much like human parents. The two parent black holes gave up their lives to form the new child. This discovery led to the Nobel Prize in Physics in 2017 for the three gentlemen I've already introduced: Ray Weiss, who taught us how to build the instrument; Kip Thorne, who taught us about the astrophysics and the theory of the sources; and Barry Barish, who is credited with leading the construction of the LIGO observatories. But my talk wasn't about this one discovery. My talk really was much grander. I said to you, this is a new window into the universe, and a single object does not a new window open. So what could we say about the new window into the universe? Well, LIGO has been operated in a series of observing runs. So let me get only mildly technical on you. The LIGO had its first observing run in late 2015, and that was when that first object, the one I just showed you, was discovered. And at that time, 2 other objects were discovered. Then LIGO shut down and made some improvements. It had a second observing run between November 2016 and August 2017. And in that observing run, our partner observatory in Europe, Virgo, also joined the run. And in that second observing run, we saw 7 more binary black holes. And then we also saw for the first time a binary neutron star collision, which I will describe. And in those 2 observing runs, we saw roughly 1 event per month. So one gravitational wave collision event or collision of a black hole or neutron star per month. And then we shut down for a long time, a little bit over a year. And when we came back with instrumental improvements, we went into observing run 3, and here we're seeing events at the rate of greater than 1 event per week. And you can see on the chart on the right, observing 1 run, observing run 2, and then observing run 3A and B, just because there was a gap between them. And you can see how quickly the number of events goes up. And this is a testament to what you can do scientifically when you make a better instrument. So the main thing was that the instrument had improved between these, the second and third observing run. So what did we see? So here are the LIGO and Virgo detections in observing run 1 and 2. So on the top left is the first one that I just showed you, GW 150914. They're named after the date that they're detected, and that was the first one we saw and the loudest. In these observing runs 1 and 2, you can see the one in the middle there. That says it was the heaviest, it was the farthest, it was the spinniest. We also look for whether these black holes are spinning on their axes. And then at the very bottom right, you can see an object that doesn't look like the rest of them. And it doesn't look like the rest of them in one very important way, which is that most of these black hole collisions that we saw, they typically last, look at the time scale in seconds, they typically last under 1 second, a few hundred milliseconds. And then we saw an object that lasted in our measurement band for over a minute. And we knew right away that that had to be much lighter and that it was likely to be a neutron star. Now, neutron stars, unlike black holes, are made of neutrons, and because of that, when they collide, that should be followed by a spectacular light show. So what did we see? On that fateful day, which was on August 17, 2017, on the bottom left, this blue and interferogram you see shows what LIGO saw. And all you can see is that we saw a signal making a track whose frequency and strength we could measure. 1.7 seconds later, after LIGO and Virgo saw this event, there was a large signal registered in the Fermi Gamma Ray telescope. So this was the first time that we saw a gravitational wave signal, and a short bit later, very energetic light, a gamma ray. Now, if indeed this was a neutron star collision and the gamma rays were associated with the collision of those neutron stars, then we should also see all other colors of light. And to do that, we had to tell astronomers with light telescopes where this object was. And by using the triangulation between LIGO's two sites and Virgo in Europe, we were able to tell astronomers that it was in a patch of sky. It was about 30 square degree patch of sky that was in the southern hemisphere. Now, it was daytime in the southern hemisphere when this signal was registered by LIGO and the Gamma Ray telescope. So astronomers had roughly 12 hours to prepare to look for something in that 30 square degree patch of sky. And what followed was what I would call an astronomer's night to remember. This is a very busy picture here, but what I want you to notice is just a few things. Over here, whether you looked in gravitational waves, you looked in gamma rays, X-rays, ultraviolet, optical, infrared, or radio, no matter what wavelength of light you looked in, you saw something. And this is the most interesting to look at. So if you pay attention to this, these panel of observations from visible telescopes, DLT-40 is a nice example. Notice that this is what was seen 11 hours after the LIGO Virgo trigger. So this is I'm trying to highlight this one here. And if you went back to that same exact field of view and you put the same exact crosshairs on this galaxy NGC 4993, you didn't see anything 20 days earlier. So a new object had lit up in the sky. So what was this? This was a neutron star a collision. And if you were to sort of visualize what it would look like, it was a pair of neutron stars. Let's see the video first. Show it to you one more time so you can pay attention. So what you see was initially the two neutron stars were orbiting each other, and the only thing they were giving off is gravitational waves, no light, and that was depicted sort of as the white space-time distortions. And then when they collided, the very first thing was a very beamed, a jetted emission of the gamma rays. So the gamma rays are very beamed and jetted. And then there was a more isotropic cloud of material that came off. And that's the cloud from which you would see many of the other colors of light, the optical, the infrared. So I can't see your reaction as to whether you'd like to see it again, but let me just show it to you one more time, just so that you can now follow what I said. First comes sort of the beam, the plumes of gamma rays, and then the more isotropic cloud of material that's the visible and infrared. Here only the gravitational waves. Now, if you measured this, the light that was coming from this object, and you measured it as a function of days. So watch at the top right of this graph, days are going by. And as we measure the different colors of light, that's what's depicted on the horizontal axis. The wavelength just says what color of light is being given off and how bright is it. You see that it's changing with time. And each of these peaks and how it's changing with time was telling us about the chemistry of what was going on inside of this collision. And one of the most remarkable things that we learned was a story about our own origins from this process. So there has been a long-standing mystery about where all of the heavier elements on the Earth. You've seen this periodic table of elements that we find here on the Earth. And you think about heavier elements like gold and platinum and the lanthanide series, there's been a mystery about where those come from. So you might ask, well, where do all elements come from? So the starting point is that elements on the planet come from their parent stars. So elements are born in stars like our own sun, for example. But stars like our own sun can't really fuse elements that are heavier than iron. They just don't have the energetics aren't right, and they're not neutron rich enough to form these heavier nuclei. So another place where people believe elements to come from, the heavier elements, would be supernovae collision. So just that process I've described earlier of when a star runs out of nuclear fuel and explodes. And that too does not have enough neutrons or energetics to form the very heavy elements. So it had long been proposed that neutron stars would be neutron rich enough and a collision would have enough of the energetics to fuse the heaviest elements. And in fact, these peaks that you see in these spectra are evidence of that. And what we find is here on the Earth, we have had more gold and platinum than is plausible to have been made in the stars in our vicinity. And therefore, the formation of heavy elements like gold and platinum, we need neutron-rich environments. Unlikely that they were formed in stars like our sun or supernovae, and therefore we have the first evidence from those peaks that indeed those heavier elements were formed in neutron star mergers. And if you look at this periodic table that's shown here on the right, the important thing to notice is that everything that's shaded in yellow is what we believe came from neutron stars. And in this one neutron star collision that we saw literally thousands of Earth masses of gold being fused, for example. So these are now also understood to be nature's gold mines. Now, in the meantime, with observing run 3, remember I told you we've had a much larger number of events that we've been discovering, and this picture on the left simply just shows you what kinds of events we've been seeing. BNS mergers means binary neutron star mergers. Those are sort of the lightish blue colors. Binary black holes are the most abundant objects that we see, BBHs, and those are the dark gray. There are, the yellow events are not real astrophysical events. They're terrestrial noise that our detector picks up. Pink events are, the light pinks are false positives in the instrument. And then the darker pink ones, we just don't know what they are. And then there's also these darker pink ones called the mass gap elements. So let me show you 2 of these that are pretty spectacular. There's many that are interesting, but 2 that have recently been announced. So on the top right, you see GW 190521. And that is the first time that we have seen something called an intermediate mass black hole. And this is a black hole system where an 85 solar mass black hole and a 66 solar mass black hole orbited each other, collided, and formed a new 142 solar mass black hole. And this has left us very puzzled. The very first black hole I showed you was 30 solar masses, and that was already a big surprise to scientists. We didn't really understand how nature makes such heavy black holes, because if we believe these black holes are formed from the collapsing of stars, stars just don't get that heavy and big without some other processes getting in the way. So that was a mystery. Where do such big, heavy black holes come from? And in fact, there was some reason there are reasons to believe that these black holes in this mass range of 50 to about 150 solar masses shouldn't exist, and yet here we are seeing them. So more head scratching. How does nature make these? Now, if you look at the bottom right, which is GW 190814, that's another very mysterious object, because I told you that the formation history of these neutron stars and these stellar mass black holes are quite similar. We believe they're both born from the collapse of stars. If the star is heavy enough, it should form a black hole. Lighter, it should form a neutron star. And there's been a gap between about 2 and 5 times the mass of our sun, where we've never observed neutron stars, and we've never observed black holes, and we don't expect neutron stars to be that heavy. And yet, we have now seen an object which has 2.6 times the mass of our sun, and it collided with another object which is 23 times the mass of our sun. So we believe this is a collision of possibly a neutron star or a black hole, unclear, because we don't expect, we don't know which it is, with a 23 solar mass object. Now you might ask, well, couldn't you just look with light to see if it's a neutron star? You should see some light. And the problem was this particular object was nearly 800 million light years away, and that makes it too faint. If it did give off light, it makes it too faint for our telescopes to see. So this is just to tell you that the field is just taking off. We're seeing more and more events. We're seeing events we do not understand. And that really brings us to what are the answers we could have, and what are some of the new puzzles. So I would say the things we kind of know is Einstein's relativity theory seems correct. We've understood that the waves travel at the speed of light. We know that gravitational waves seem to have the expected geometry in terms of space-time distortion. We know black holes exist and they even form pairs. We're not really sure how they form pairs. So mysteries. How does nature make such heavy black holes? We don't know. How does nature make them in form pairs? Do these form pairs because they're born as twins in a binary system, so binary stars that collapse? Or are they just random black holes floating out in the universe that meet each other and get gravitationally bound? We don't know. How might we find out? Well, one of the ways we'll learn about that is by looking at the spins of black holes. So if you have dynamical capture where two black holes just randomly meet each other, then their spins should be randomly oriented, because there's no reason for one black hole to meet another black hole whose spins are exactly aligned. They can be randomly oriented, and that would tell us about that formation scenario. On the other hand, if you find black holes whose spins are always aligned with each other or anti-aligned as they spin about their own axes, then it's very likely that those were born in a system together, because as they transfer mass to each other, that mass transfer tends to align spins. So those are the kinds of questions that we could start to ask. Now, so I hope I've kind of made the case that first discovery was only just that, a first discovery. But in the meantime, we've had these direct detections of gravitational waves. We've, confirmed Einstein's theory. We've seen multiple black hole and neutron star binary collisions. We're continuing to look for other objects that I haven't had time to talk about. And I would say this is a personal note of mine, as someone who spent all of my career building an instrument that was precise enough. It was really, really great that to achieve, at a sub-atometer precision with the instrument as well. And all of that put together, we are seeing the birth of a new field. I really want to make that very clear to you. We've turned on a completely new way in which to study the universe. We no longer need to use gravity. We no longer need to use light, rather. We can also use gravity alone or in conjunction with light as a new tool for unimagined discoveries. So I'm going to leave you with one last thought about how to think about this field. And that is to think about Galileo and the telescope. So Galileo, we believe, was the first person to point the telescope at the sky. And Galileo's telescope in 1609 was this 1.5-inch refractor. I mean, most decent toy store telescopes can surpass that. And Galileo observed things within our own solar system. He observed the craters on the moon, observed the phases of Venus. Really, nobody remembers or what exactly Galileo observed other than the experts. But what we do recognize was the paradigm shift that Galileo made. What Galileo showed humanity was that we no longer need to look to the sky just with our naked eye, that we could use instruments to assist us in looking deeper into the sky. And since the time of Galileo, we've built 100-inch telescopes on the Earth. This is Mount Wilson, which was built in 1917. We've put 100-inch telescopes in space, which is the Hubble Space Telescope. We are now building 25 to 30 meter class telescopes here on the Earth. This is a picture of the giant Magellan telescope. In the meantime, we've also turned on other colors of light, not just what our own eyes could see, but we've built telescopes that can see infrared, that can see gamma rays, that can see X-rays, that can see radio waves. And that's how we've put together a picture of our universe so far. So I'm going to leave you with this final thought, that when you think about the universe in gravitational waves, it turns out gravitational waves also come in in a full range of colors, if you could color code them. They span 20 orders of magnitude in wavelength, very much like light. And what we have done with these Earth-based observatories like LIGO and Virgo is at the very rightmost end of this graphic, at the objects that are moving are small and light, small and light, we know there's still many tens to hundreds of solar masses, but they're moving and orbiting each other at very high frequencies, 100 hertz or so, or millisecond timescales, and that's what we've seen. And there's a whole set of other detection methods, from looking at putting these kinds of interferometers in space, to looking at the timing of pulsars, to actually looking at the earliest light in the universe, which is the cosmic microwave background and its polarization, to construct what the universe looks like with gravitational waves. So I want to leave you just with this idea that, you're witnessing the birth of a field. No one would have thought that Galileo's modest telescope would lead to what it did 400 years later. And I'm really excited for what the future will bring with this tool. So thank you for listening. I'll take questions.
Thank you very much, Professor Mavalvala. I think there has been an enormous amount of appreciation expressed already in the chat and YouTube, and also in Zoom. Please continue to express your appreciation for the talk. I'm sure Professor Mavalvala will like to see it later, if not right away. It's unfortunate we can't give you some kind of auditory feedback, but I can tell you the response has been very, very overwhelmingly positive. And we've had a lot of interesting questions come in already. Super. So I'll allow you to drink a short bit of water, and then we can get straight into the questions if it's okay with you. Is
Absolutely.
All right. Yep. So the very first question we have came from the chat in the Zoom session. Mm-hmm. And that question is, why is it that you don't use lasers with higher frequency in the interferometer? I would naively expect, e.g. UV, to make the small length easier to be measured.
Yeah, so that's a really good question. Yes, so you're right. If I tell you that the wavelength of the light is the tick mark on my ruler, then having a smaller wavelength of light would actually make my ruler more precise. It turns out we don't, because UV lasers are not, or even just lower wavelength lasers are not stable enough. And what that really means is that you can make your tick marks be closer, but they're jittering more relative to each other. So we use the lasers that we do. These are solid state near infrared lasers, because they're the most stable lasers that we can find. So we need two things. We need them to be reasonably high power, and we need them to be stable. And those two criteria are fulfilled by these lasers that are optimal at roughly 1 micron. So it's a good question.
Thank you for that answer. We have many more questions. I'm going to go back and forth probably between YouTube and Zoom. So that first one came from Zoom. I'll go to YouTube for the next one. So the next question comes from YouTube. The question is, do gravitational waves interact with other gravitational waves, like electromagnetic waves?
Yeah, so I think you can think of them very much like any other wave. So they do interact, and the reason why it's just like light waves in the universe, uh, they're not emitted coherently from different sources. So they kind of just pass through each other. But if you had a coherent emitter, they would do all the usual things. They would interfere, they get redshifted, they change their wavelength as you observe them relative to a moving source. All of those things they do, just as you would think of other waves.
Thank you very much. We've had a request that you unshare your screen so that we can see a little more of you when you're answering the questions, if it's possible.
Sure, why not?
Great. Okay. Now I think I'll go to a question from the Zoom session. So just a reminder to everyone in the Zoom session, if you would like to ask a question in person, you are free to raise your hand icon, and that will bring you up to the top. And then I'll pick you one by one and ask you to unmute yourselves. You should have the power now to unmute if I ask you to. The first question on my list, it's from Griffin Schwartz. Griffin, could you please unmute yourself and lower your hand when you're done asking the question? Turn on your video if you would like.
Yeah, can you hear me? Oh, there we go.
Yep.
Great. So from my knowledge of particle physics, I know that if we try to probe smaller length scales, we need higher and higher energy because of the uncertainty principle. So how do we get around that if we were measuring a really small distance with a relatively not very energetic wavelength of light?
Yeah, so look, the uncertainty principle is very much alive and well in these measurements as well. So what we do is, if you think about how the uncertainty principle plays into this measurement. So what's the principle of the measurement? The principle of the measurement you can think of as simple as saying, I shine a beam of light at a mirror, and then when the mirror reflects the light and comes back to me, and I measure how long it took. Now, in reality, I measure a phase, which means I'm measuring just relative, travel time. And what we do is we encode that relative travel time of light beam in this L-shaped arm versus that L-shaped arm into an output that's proportional to the number of photons we measure, right? So that's it. If we have total destructive interference, we know what distance it is, and then a little bit more. And so the quantum limit comes from our ability to resolve small changes in the number of photons we're measuring. Now, this is a very simplified way to say this, because in reality we are measuring something like 10 to the 22 photons per second. So it's not that we're measuring 1 photon versus 2 photons, but what we are still measuring is we're measuring 10 to we're measuring at the shot noise or Poisson limit. So if we have a certain amount of power, the noise in our measurement given by the quantum limit is the square root of that power. And that's why we are always tempted to go to more and more power in our measurement. Now, it turns out the uncertainty principle does come back and bite you when you do that. And it bites you in the following way. So you're tempted to increase the power because that gives you more resolution on the number of photons you're measuring. But as you increase that power, which means increasing the number of photons you use in the measurement, you have more photons hitting the mirror, and those photons also carry momentum. And so the momentum, the radiation pressure of the photon and the fluctuations, the quantum fluctuations, the number of photons now gives you kicks to your mirror. And that's the uncertainty principle right there. You're tempted to use more photons to make a more precise measurement, and the uncertainty principle then says you have to pay a price, and the price is I'm going to disturb your measurement. So it does play. So, and if you ask this in terms of energy, you can make the same argument in terms of energy and time. Whether you make it in terms of position and momentum or energy and time, the uncertainty principle is at play here. And I will address that quite a bit in my science talk tomorrow.
Okay, thank you very much. I think we have many more questions to go through, so maybe we can go to a YouTube question. The next YouTube question is, you've observed black hole mergers and neutron star mergers. What is there left to learn using LIGO and other planned observatories? Yeah, so look, I'll say neutron star mergers and black hole mergers were sort of expected. This is what, these are objects that we've been able to
predict we should be able to see. There's been a lot of uncertainty on how many and where they would be and how heavy, etc. But they're very much objects that come right out of Einstein's theory of relativity. The things that are remaining that we know to look for are things like supernovae. So supernovae is a very beautiful example of something where we expect when a star goes supernova and you see all of that accelerating material that's coming out, mass that's coming out of it, that it should emit gravitational waves. And there's a lot of excitement to be able to see that, because the gravitational waves are quite they're quite transparent to matter. So we expect that they will come out of the core of the supernova before the light does, and will give us some measurement of what's going on inside before the actual light can tell us. So supernovae. So I'll give you, there's also the things we don't know what, are out in the universe, which I fully expect we will discover. That's been true every time we've turned on just a new color of light in a telescope to look out into the universe. We've discovered objects we didn't know existed. But I'll also give you another example of something that's really, it's the thing that drew me into the field, although I don't believe it's the thing that will be measured by these kinds of instruments, these interferometers in my lifetime. And that is gravitational waves from the very early universe. So one thing that I didn't get to say is, one of the power of doing astronomy with gravitational waves is that gravitational waves pass through everything quite undisturbed. You can think of them just as you might think about going to a party, for example. If you go to a party with an extrovert, and light is an extrovert, what you would do is you'd say, okay, I'm ready to leave, and your friend will take an hour to get out of the room, because they stop and they talk to everyone and they say goodbye and then zigzag on the way out. And by the time you get out, it's an hour. And that's what light does. Light interacts with matter very strongly. It scatters off of matter. Gravitational waves are extremely aloof. It's like going out with an introvert, and you say, I'm ready to leave, and you're lucky if they'll say goodbye to the host. They're straight out the door. And so they bring information from the systems that they're in, and in particular in the hot, dense early universe, when it was too hot and dense for light to escape, gravitational waves have been streaming to us from the very beginning. So if you look at light, the earliest information that light can give you about the universe is when the universe was about 400,000 years old, whereas gravitational waves, as LIGO was sensitive enough to see these gravitational waves from the early universe, they would be from the time when the universe was 10 to the minus 22 seconds old. So that just blows my mind that you could look that far back to the beginning of the universe with this tool. Now, I will admit, for an instrument like Advanced LIGO, we're still, a factor of many thousand to a million away in sensitivity, and that's why I'm not so optimistic that this will get done in my lifetime. But just think about Galileo's story, right? Look where we've gone. So those are the kinds of things that we can be excited about. Primordial black holes, people don't really know, what they're about, and maybe we'll see those. Really crazy ideas also include things like wormholes, and I call them really crazy ideas just because they're science fictiony. But again, today's science fiction is tomorrow's science.
Thanks a lot. That was a fantastic response. For the benefit of people on YouTube, Professor Jack Childress Sankey's response to this was, I remember parties. I think he's reminiscing very fondly with toddlers at home and maybe with the pandemic. So our next question will come from Zoom. Professor in the physics department, Jim Klein, could you please unmute your microphone, turn on your camera?
Hi, thanks for that wonderful talk. And maybe you're going to tell us about this tomorrow, but could you say a little bit about what's on the experimental horizon? Because LISA's quite a long ways away, and I wondered what's going to be between LIGO and LISA.
Yeah, so LISA is, so let me just say, yes, I will say more about this tomorrow, but I can also say a little bit right now. So LISA is the laser interferometer space antenna. So it's a space version of the, it's a space-based interferometer. And what LISA is able to do is LISA is able to measure gravitational waves that are much slower, much lower frequency than the terrestrial, the Earth-based detectors. So LIGO and Virgo, their best band, their most sensitive band is right around 100 hertz. You can think of, so when these black holes and neutron stars are whipping around each other at 100 times per second, that's the thing we can observe. Now, if you think about things like supermassive black holes, which we believe are at the centers of of most galaxies we've observed, and you think about those black holes merging as galaxies merge with each other, those objects are million to billion times the mass of the sun, and they are not whipping around at 100 times per second. They are more kind of in the millihertz range. And LISA will be able to detect those. So you can think of, when I think about LISA and LIGO, for example, or LIGO and Virgo, I think of the same way as you might think about an optical telescope versus a radio telescope. It's a lower wavelength measurement of gravitational waves of lower wavelength, so different sources. LISA has had a great deal of success on its Pathfinder mission. So there was a space mission to test out LISA's technologies that demonstrated that LISA can achieve its technical goals, and it has a launch date of about 2034. Now, in the meantime, on the Earth-based detectors, there's a program to make improvements. So if you recall, during my talk, I showed you this graph of what happened in observing run 1, 2, and then in 3, the number of detections really took off. And that's a program of improving the instrument, in some cases, introducing new technologies, and some of which I will talk about tomorrow. And then you can make those kinds of improvements to advanced LIGO, for example, or advanced Virgo, probably out to the end of this decade. And then what you're going to find is that to do better and to do substantially better, the technologies become either prohibitively expensive or just too hard. And so there's a program across, in the US and in Europe of the conceptual designs for third generation detectors. And one of the knobs that hasn't been turned on these detectors in 4 decades that we're now ready to turn again is to make them longer. So these are conceptually 10 to 40 kilometer long detectors with a number of new technologies going in. And so, and those are kind of, those are also on the sort of the 20-year time scale. They're just, the technologies are being tried, they're conceptual, they're not funded. So, but that's where the field is going. There's the space detectors, and then there's these third generation, tens of kilometer long Earth-based detectors are the 2 directions that are going on.
Thank you very much.
Thank you.
Okay, thanks for the question, Jim. Please lower your hand if you're done. The next question is going to come from YouTube. Here it is. Let me just read it again. So the next question is, how are researchers at LIGO able to extrapolate the source or origin of the gravitational waves from their detector? Does having multiple detectors work together improve this quantity?
Yeah, so let me say something about that. So the answer is yes and yes. So how do we tell where, how do we tell the properties of the source? The properties of the source are encoded in that chirp signal for these binary systems. So I showed you a little cartoon of how by looking at the frequency evolution, you can tell what the mass of the system is. And then by looking at the amplitude, you can tell how far away it is. And so those are the ways in which we get sort of the intrinsic parameters of the source. And that, interestingly enough, is all encoded in that waveform, because the waveform has so many properties. In terms of where it is located in the sky, that is totally done by triangulation. And that's part of why we have a network of detectors. So gravitational wave detectors, you might have heard this analogy that, oh, gravitational waves are like listening to the universe. And that's because it turns out that the signals we are looking for from these sources happen to be in the human audio band. So you could encode them. They don't really make a sound, but you could encode them to sound. Well, gravitational wave detectors are like our ears in one other way, which is they're not very directional. So, just like our ears, our eyes can, spot a dot somewhere, but our ears cannot tell you exactly where a sound was located. They do use triangulation. Gravitational waves do the same, or detectors do the same thing. So having more of them and having them separated spatially as are the LIGO ones and Virgo, and that's one of the big motivations for a detector in India, to get one that's also spatially separated from those is how we locate sources in the sky.
Okay, thank you. Here's an interesting question. So as gravitational waves pass us, do they leave any long-term permanent changes to our solar system or to our galaxy's direction, movement, or any other lasting effect?
Yeah, so look, there are certainly ideas out there, even within the general relativity framework of memory, that space-time has memory, and that after the wave has passed, it ever so slightly leaves the space-time different than it was before, just like in elastic materials. And once you pass a certain elasticity, it deforms the material permanently. So there are ideas about that. I can't tell you a whole lot about them. I'm not sure. People certainly use LIGO data to look for that as well. So I'll say that.
Okay, we have a bunch of questions. I think I might just go for one or two more and then we'll call it a night. So we have one more from the Zoom session. This is, how will space-based gravitational wave detectors allow other objects to be detected?
Yeah, so I spoke very briefly about LISA, and how LISA is very much, it will look for different kinds of objects. So LISA will be able to observe the mergers of supermassive black holes, for example, which LIGO simply can't do. Those occur at frequencies that are too low. LISA will be able to see a background of white dwarfs, which are another kind of object. So these two observatories really do target different astrophysical populations of objects.
Okay, let's do one more, and then I think we've got to call it a night. So this question is, you mentioned that the frequency of gravitational waves spans over several orders of magnitude. Could you give examples of what events will cause them?
Yeah, so I think the two examples that I've already given are the following, right? So we know LIGOs, these are stellar mass, so stellar to tens of stellar mass black holes, they can orbit each other fast enough. Then you get down to sort of the tens of, so that's 100 hertz-ish. Then you get down to sort of 100 millihertz, that's the LISA band. And there you can see supermassive black hole collisions. You can get down to, basically you get down to wavelengths that are sort of the size of the universe wavelengths, and those are these very early universe gravitational waves from the birth of the universe, if you will. And then there's also sort of a nanohertz range where there are gravitational waves that you can detect from measuring the timing of these pulsars. So remember I told you pulsars are nature's lighthouses. They also, as many pulsars are extremely stable. They rotate at a very fixed frequency. And so by measuring small perturbations in the frequency of pulsars, because of gravitational waves passing by, you can learn about gravitational waves at those wavelengths as well. So those are sort of the known ones. There's a whole range of other observations and sources that people talk about.
Okay, thank you very much. Thank you for this fantastic talk and the fantastic question and answer session. I really enjoyed it myself. So I think from what I see in the YouTube chat and the Zoom chat, others really enjoyed it as well. Please continue to write great things in the YouTube chat and in the Zoom chat. I will share the Zoom chat session with Professor Mavalvala after the talk, and she'll be able to watch the YouTube chat afterward to enjoy all of your wonderful comments. And I'll just remind everyone to come back tomorrow to see Professor Mavalvala give a scientific lecture in the form of a departmental colloquium at the usual colloquium time, 3:30 p.m. Eastern. And it will be again on the same YouTube channel or the same Zoom link that you've been sent. And I hope you can all make it.
So I just want to thank everyone also for coming, and thank you, Bill and Jack. Thanks so much. This has been fun, and your questions were great. So thank you.
Okay, thanks a lot. I'm going to stop the live stream now, if I can click. Oh my goodness, some disaster.